My name is Tsubasa Takahashi, Machine Learning Research Team. Differential privacy in machine learning is my topic. So in this session, I would like to talk about the differential privacy's overview and basic items. And also would like to talk about how to make differentially private. And then finally, want to talk about differentially private deep generative models, which is our achievement of the research. First, basic item of the differential privacy. Hopefully, I would like to be clear to those who without a mathematical background. In line, by leveraging various data, we are making the improvements of business every day. Under such data usage, privacy is a key item to be paid respect. Differential privacy is the privacy standard recently attracting attention, and the analysis of the data collection and the results sharing in many scenes, the privacy protection is using this differential privacy. At our team, differential privacy is regarded as a key technology to protect privacy of users, of the massive amount of users as well as the data, which is the privacy at line scale. And what is the differential privacy? This was proposed by Microsoft Synthesized work in 2006. WWDC 2016, Apple said as in the screen, the completely private is an expression which has a room for discussion, but in a nutshell, hashing or subsampling or noise injections and other type of randomization is done, and those statistics and machine learning will be realized and to pay attention to the privacy. Already, Apple and Google leveraging the data or statistics from your smartphone by having the privacy in place. And in this differential privacy was adopted in the U.S. Census 2020 to protect privacy. In the census of the U.S., they have been working on the potential options of the privacy protections. And at the time of the release of the 2020 U.S. Census, the U.S. government would say that the new gold standard in data privacy protection, they will adopt the differential privacy. So this would be the precursor to other countries to be adopting this differential privacy, and other services may using this differential privacy for the questionnaires and so forth. So in a nutshell, 3 sentences describe differential privacy. Privacy for stats and machine learning, privacy by randomization, privacy at scale. Especially the third one, privacy at scale, is critical. As the data volume goes up, even though the analytics can be performed with the limited degradation. So starting here, I would like to touch on the differential privacy in details. For the basic form, as you can see, described on the left-hand formula. Allow me to speak. I will describe that it means that the output of algorithm does not depend on influenced by specific data. So that means that, in other words, it is difficult to guess from various data from outputs. So privacy parameter epsilon is used to control the level of difficulty to guess. So this differential privacy is achieved through the noise injection and other randomization. Talking about the privacy protection, people may think about encryption or secure computing, but unlike encryption, once randomized, cannot be returned to the original source. That is a key feature, one of the key features of the differential privacy. So I want to show you the example of the histogram randomization. On the left, you can see the graphic is the histogram of data D and D dash with only one record difference. By comparing the two, you can identify Alice is in the group of B, identified Alice. And on the right, both histograms are randomized. Through this randomization, even with or without Alice, similar result is provided. That means very difficult to detect Alice data. Let me explain how privacy parameter affects using randomization via flipping a coin. So the approach is to show true value when heads appear, and the false value is shown when tails appear. So here, the assumption is that odds of having heads or tails are weighted like this exponent function. Epsilon equals to 0, the odds of heads, tails appear is 0.5, which is equal to random guess. Same as random guess means that the sensitive data inputted is completely not dependent on, therefore cannot estimate the input from the output. So differential privacy is epsilon 0 is the most privacy is protected. So if the epsilon value goes bigger, then odds are higher to be detected. So of course, a few times of output rather difficult to guess, but according to the value of epsilon, then the possibility would become higher to be guessed. So infinite value of epsilon means this always the definitely true value. So almost no privacy protection. So in the privacy arena, this how to set what kind of value of epsilon will be set has a kind of discussion, but between 1 to 4 is the likely to be used in a scientific arena. Next, privacy at scale. To show privacy at scale, very simple data analytic result is shown here. These diagrams show the assessment result of frequency estimation by randomized 100 sorts of items. The blue bar shows the true frequency, orange bar shows the randomized data and assumed frequency. And in each evaluation, 10,000 and 10 million artificial data was used. As you can see, in proportion to the data volume, error of frequency estimation goes down. So that means that as a platformer with the many users, even there is a certain privacy protection randomization, very high usability or serviceability is obtained and by gathering data and utilize. And through the R&D of the differential privacy, I would like to achieve the trustworthy data platform. This trustworthy data platform, one thing I would like to achieve is the data statistics or AI will be shared by protecting privacy. These days, so-called dark data, which is unused data, are retained and stored in the corporations, many corporations. One of the reasons for that unused data is the privacy. So through the differential privacy, if the hurdle can be alleviated, then knowledge can be leveraged and circulated across services, and insights can be shared with reliable partners. And going forward, many AI will be deployed in our society. However, in reality, there are many threats exist. So it is easily imagined that some people try to exploit sensitive information by attacking AI or AI developed with malicious intention. Under such a wild environment, to protect AI, differential privacy can be effective to a certain level. Second, I would like to achieve is to have the census type of questionnaire to be conducted in order to understand users more. At the time of the COVID-19, LINE conducted a questionnaire which participated by many users, and I personally was not able to be involved in this questionnaire. But if at that time, if we were able to show the reliable, trustworthy result of differential privacy, then we could have been able able to raise more in-depth questions to many more users. I've been involved in this research in the past 10 years, so I'm very, honestly sorry for not being able to contribute. But even under the different environment, by the differential privacy to be utilized, the user's voice or real behavior can be obtained, of course paying attention to the privacy, and then leverage those data to the better quality of service and satisfaction. And to realize such a trustworthy data platform at Line, which attracts so many users, I will continue to work on the differential privacy research going forward as well. Next, I want to talk about how to make the differentially private approach. So, in order for you to understand our research results, I include some introductory remarks. So, the way to learn the differential privacy is there are two ways. First is learn as usual without randomization, and random response mechanism is applied at operation. As a use case for this, MLRs, machine learning as a service. So the model must be put on a secure location and accessed via API. In this approach, you don't need to know specific knowledge about the model learning, but the model itself is not differentially private, so it's not appropriate to share model. Number two approach is the randomization while learning. Against the model parameter, differentially private, so that is the one benefit. Therefore, it is applicable to a use case to share model. To achieve this approach, one framework is DP-SGD. I would like to touch on this DP-SGD in the following slides. DP-SGD, or Differentially Private Stochastic Gradient Descent, is a framework of privacy-protecting type machine learning, where randomization that assures the differential privacy is employed. So DP-SGD randomizes adding noise to gradient used for parameter updates. Updating parameters with randomized gradient parameters are also differentially private. Let me explain how to calculate the DP-SGD. First, B units of data is randomly sampled from training data to create mini-patch. Randomized gradient by adding Gaussian noise and others after calculating losses and gradient of each patch. Privacy consumptions at each parameter update iteration is derived with rho, sample rate, and sigma and noise scalar. How much noise should be injected? Then, differential privacy, the key concept is sensitivity. Sensitivity shows how much function shows output would differ when changing a sample in batch. Therefore, adding noise showed in the sensitivity can cover up any single sample change from the output. So in DP-SGD, noise is added to the gradient, so gradient sensitivity must be identified. However, gradient the sensitivity definition is quite difficult. The gradient size gets very big or small depends on the progress of learning. DP-SGD employs clipping L2 norm of the gradient by a constant c to bind the gradient size. With this clipping, gradient sensitivity is set as a constant c, and differentially a private gradient can be built by adding noise proportional to a constant c. To learn a model using randomized gradient with DP-SGD, we'll randomize parameter updates. However, the noise for randomization is sampled from Gaussian distribution when mean equals to 0, variance sigma, and the impact of noise becomes smaller by repetitive updates. On the other hand, a differential privacy with the DP-SGD to be combining epsilon, which is the privacy level by each update. So it means the level of privacy to be assured will go down when more updates are performed. Therefore, the privacy budget needs to be defined in advance, and updates will continue until the privacy budget is exhausted in learning process. That is about the DP-SGD. In this part, I explain in the machine learning to achieve the differential privacy, DP-SGD was briefly explained. Using DP-SGDs, you'll be able to acquire various machine learning model parameters by protecting privacy. Through such a privacy protection technology, machine learning model, AI, are built using privacy data, personal data, with the paying attention to the privacy.
In the second half of the session, I will introduce the latest research results of our research team. The research I am presenting today is the result of a joint research with an intern last summer. The papers and codes are published on arXiv and GitHub, so if you're interested, please have a look. The motivation for this research is to utilize a generative model that guarantees differential privacy as a means of sharing sensitive data while protecting privacy. The business departments that receive the generative model can freely generate pseudo-data from random numbers. What is important here is that you can generate useful data while protecting privacy. That is, you can hide the individual characteristics of sensitive data while maintaining the overall trend. Our research is based on VAE, Variational Autoencoder. By learning VAE while protecting privacy and sharing only the learned decoder, the recipient can generate synthetic data using random numbers. The reason I used VAE was because I wanted to utilize the high expressive power of neural network. Especially in this research, I wanted to realize a generative model that works well for high-dimensional data, so I started with a method using a neural network. We also examined GAN, Generative Adversarial Network, which is the most well-known method for generative models, but it was difficult to train by a DP-SGD-like method because it is not easy to converge the learning of GAN. Also, it was not easy to maintain the inherent characteristics, trends, and distribution of the dataset due to mode collapse. That's why I chose VAE over GAN. Before explaining the proposed method, let me share some of the results achieved by the proposed method. Here's the result of learning the generative model and randomly sampling the handwritten character data of MNIST, which is often used in machine learning. The first from the left is the original MNIST data. The three generative models compared here are all based on the variational autoencoder. VAE plus DP-SGD is a simple method of training the variational autoencoder using DP-SGD. This simple method is strongly affected by noise and cannot produce a clear sample. DPGM is a method that implements preprocessing by clustering. We were able to generate data with relatively little noise, but the inherent characteristics and diversity of the data have been lost. The final result is the one achieved by our proposed method. We have confirmed that it is possible to generate data with less noise and with diversity close to the original data. The contribution of this research is that we have achieved the following 2 points with generative model guaranteeing differential privacy for the first time: to have robustness against noise so that generative models of high-dimensional data can be also learned, and to generate high-utility data maintaining the distribution of data. Then, why is it difficult to learn the generative model while guaranteeing differential privacy? Our insights are the following 2 points. First, due to privacy budget constraints, learning needs to be completed with little epochs as possible. Second, the inserted noise makes it difficult to learn multiple tasks at the same time. In VAE, encoding and decoding are trained end-to-end, but this might not be easy under the constraints of differential privacy. Let me explain the training process of VAE with a simple diagram. In encoding, it learns the mapping from the original data to the latent space. In decoding, it learns the reconstruction of low-dimensional latent space into original data. In VAE, this encoding and decoding are learned end-to-end at the same time. Next, let's look at learning VAE with DP-SGD. As I said earlier, DP-SGD adds noise to the gradient and updates the parameters. Therefore, displacement due to noise occurs in each layer and parameter of the neural network. In encoding, AI needs to learn the mapping to different spaces, but noise makes it difficult to stabilize the coordinates to be embedded. If you try to learn the reconstruction from unstable coordinates at the same time, the deviation will be even bigger. The approach we have taken to overcome these challenges was straightforward. We stopped learning end-to-end and introduced a very simple two-phased algorithm. Our proposed method is called P3GM, Privacy Preserving Phase Generative Model. As mentioned earlier, AI will learn generative model that guarantees differential privacy using two-phase learning algorithm. Phase 1 will be in charge of the task corresponding to encoding. To simplify the encoding, I wanted to replace the underlying latent space with something that could be embedded in a simpler way. One way to do that is to make the latent space the original data space itself or a compressed version of it. This makes it easy to obtain embeddings, for example, with compression methods such as PCA. In this study, we introduce embedding by DP-PCA and estimation of prior distribution by DP-EM. In phase 2, the embedding acquired in phase 1 is fixed and only the reconstruction is learned. That is it. The important point is that the embedding obtained in phase 1 is fixed so that it can concentrate on the learning of the reconstruction only, so that the plausible reconstruction can be achieved with a limited frequency of learning. Compared to the end-to-end learning method, this two-phase learning has a lot to lose in terms of optimality. However, considering that learning itself didn't go so well before, I think this method is one of the valid heuristics. Please refer to the paper for a detailed consideration of this method. Finally, here's the evaluation of this proposed method. First, we evaluated the accuracy of the classifier learned using the generated data. Second, we looked at how efficient learning has become. Third, it shows how robust it is against noise. we evaluated how much utility of the data in data mining was maintained when using the sample data from the generative model. This evaluation evaluates the performance of classification for 6 data sets. For comparison, we used VAE-based DP-GM, Bayesian network-based Prive-Bayes, and Ryan's method, which won the NIST data synthesis competition. For high-dimensional image data such as MNIST and Fashion MNIST, our proposed method, P3GM, shows performance comparable to non-private VAE. The 4 data, such as Kaggle credit, are datasets of tabular format. Against those, we can see that our proposed method shows very high performance in many tasks. From the above, we can say that the proposed method achieved a generative model that guarantees differential privacy while maintaining high utility. Next, we evaluated the efficiency of learning. The proposed method simplifies learning, so it is expected to be highly efficient. The left graph shows the reduction in reconstruction error. The proposed method shown by the orange line can reduce the reconstruction error faster than the naive method shown by the blue line. The right graph shows the classification accuracy of the classifier learned from the generated synthetic data. We can see the proposed method presented by the green straight line achieved high classification accuracy at a very early stage. From these results, we confirmed the high efficiency of the proposed method. Finally, in order to evaluate the robustness against noise, we measure the classification performance when the privacy parameter epsilon is changed. The smaller the privacy parameter epsilon becomes, the demand for privacy becomes higher and the noise becomes louder. The proposed method P3GM, shown by the orange line, shows very high classification accuracy in epsilon 0.1 and 1. Generally, it is considered that privacy protection is sufficient if epsilon 1 is achieved. Therefore, I think that the proposed method has a high enough robustness against noise that can withstand practical use. The blue straight line in this figure is a reference showing the performance when P3GM is not privacy protected. As you increase the epsilon, you can also see that the orange P3GM approaches the blue PGM. From the above, it was confirmed that the proposed method has high robustness against noise. Here's the summary of my presentation. In this session, I shared the basics of differential privacy. Differential privacy is a privacy protection measure through randomization, and it is suitable in this big data era because the effectiveness increases in proportion to the size of the data. In the second half of this session, I shared our research result, P3GM, a generative model that guarantees differential privacy. The proposed method, P3GM, is a learning method for a generation model that is robust against noise using simple two-phase algorithm and has shown high utility in data mining using generated synthetic data. Our research results shown in this session are published on arXiv and GitHub, so please take a look if you are interested. And details of this research will be presented at ICDE 2021, which is the top conference of data engineering and data mining in April 2021. Here are the references used in this presentation. That's it. Thank you very much for your attention.